Okay, good afternoon, everyone. Are we live, Geraldo? And I'm audible in Zoom. Okay, great. So today I'm lecturing on behalf of Professor Onur Mutlu. Unfortunately, Professor has some issue with his voice, and he asked me to deliver today lectures. So today we are gonna first continue what we have studied yesterday about Verilog. The main focus today is about how we can use Verilog to implement sequential logic. And after that, we have, the second part of today's lecture is about timing and verification, which is quite important. And we're gonna cover also. So yeah, as I said, the agenda for this lecture is about continue the HDL, and we're gonna see how we can implement sequential logic in Verilog. And as we already said, these Verilog slides are kind of tutorial, and you can basically, you will be learn a lot and use them for your labs. So basically all the slides will be beneficial for your labs. So as a kind of, quick recall, why we need a specialized language for hardware. The main reason is that when you want to model the logic design, basically you have some definition there, like gates, wires, combinational logic, complex logic, and also the way that you want to interconnect them. And also the notion of basically concurrency that you have in the hardware. So all these things are already implemented in HDLs. And that's one of the main reasons that it's easier and more efficient to use HDLs to implement logic. So, and we learn as an example, HDL, we are learning Verilog. Yeah. So basically for HDL, we have structural or gate level HDL that we covered actually mostly yesterday. And also today we are gonna see behavioral HDL. So structural and gate level, as a quick recall, is basically when you want to, the body of the module is basically using gate level. You use gates and instances of gates, and basically how do you interconnect gates so that you can implement your logic. But we also have another way to implement Verilog code, which is behavioral. Basically, the module body contains functional description of the circuit and contains logical and mathematical operators. So basically, the level of abstraction is higher than the gate level or structural level, which makes actually programming easier. So in reality, basically, many practical design use a combination of structural implementation and behavioral. And you know that basically when we model a hardware using HDL, in the end, we also want to synthesize it. So there are many tools that basically they are synthesizing your HDL description for a certain specialized, for a specific circuit. Could be FPGA, for example, in your lab, you're already, I'm not sure this week, yeah, you are gonna see, I guess next week, that you're gonna use Vivado that can basically synthesize your HDL description for FPGAs. There are also other tools that you can basically use to synthesize your logics. So, and basically synthesizing tool, they do a lot of optimizations, but they cannot basically guarantee that the solution and what they reach in the end is optimal, which is basically due to computational expensive placement and routing. And also you want to simulate your circuit. So there are also tools that you can use to simulate what you already described as HDL. And that's important because you want to verify your circuit. And we will see, hopefully today, how we want to verify circuits. Okay, so now let's see how we can implement sequential logic using Verilog. So as a quick recap, any sequential circuit can basically consist of two important, let's say, components. One is a combinational circuit, and the other one is storage element. So basically, you need a storage element to store the states of the circuit, and also you need some combinational circuit in order to define what is the next state and also what would be the output. So if you are, for example, designing a sequential circuit following by Moore, you know that basically the output is always dependent only on the state. So basically, we need a combinational circuit that we give to that combinational circuit as an input the current state, and the output would be the output of the circuit. And also, in order to see which the next state, so in Moore, the next step depends on the current state and the input. So we also need a combinational circuit for that. So basically, it's always good to know, to remember that sequential circuit is combinational circuit plus memory. So when we want to describe hardware that has memory, we need flip-flops, latches to basically implement FSM. So sequential logic state transition is triggered by a clock. So basically, latches, they are sensitive by the level of clock. So you can have a positive latch, which is sensitive by when the clock is full 1 or high, and also negative latch that basically is sensitive by the level of 0. And we also have flip-flops that you already, I guess, know that is dependent on the rising edge or falling edge of the clock. So combinational HDL constructs that we already, covered yesterday, they are kind of not sufficient to express sequential logic. Actually, we can express the flip-flop using a structural level, but that's not efficient and easy to do. So in order to make it easier and more efficient, we need new constructs in Verilog, which we are going to see is about block, always block, and also some definition as postage or negage. So the always block is actually written like that, is syntax there. So you have this always at a sensitivity list. And basically the sensitivity list, you're basically making some expression that whenever the event in the sensitivity list occurs, the statement in the always is going to execute it. So the flip-flop, this is what you, I guess, learned, how we can make it the flip-flop. So when the clock is low in this, so this is master-slave latch, right? So when the clock is low, the first latch propagates D to the input of the second, latch, which we call it slave latch. And only when the clock is high, the second latch is going to propagate, or let's say store, store Q to D. So as the rising edge of clock going from 0 to 1, you can assume that Q gets assigned D. So stage changes on clock edge, and we know that data available for full cycle. So at the rising edge of clock, we all know that we're gonna move to we will store the input in the flip-flop. And this is how we basically show flip-flop in the circuits. That triangle shows that we are basically sensitive by the edge of the clock. Here, because there is no, let's say, circuit, is rising edge, but it could be also falling edge, which we call it, falling edge or negage of clock. So we use the flip-flops to implement the state register. So the way that we implement flip-flop in Verilog is using always. And in the sensitivity list of the always, we put @ postage clock. That can basically, whenever you have in rising edge of clock, you store the input in the flip-flop. So yeah, this is basically how you define a flip-flop or a register here, because here we have 4 D flip-flops because the input and output are 4 bits. So yeah, I already covered this. So it's important that you can see we don't use assign a statement that you already learned yesterday, I guess, in the always block. So you cannot write assign something, blah, blah. So that's important. It's actually a syntax error in Verilog. And another important thing is that we are using this expression, less and equal, which is describe a non-blocking assignment. We will learn later in this lecture that what's the difference between non-blocking assignment and blocking assignment. And another important point for Verilog is that everything that you have in your always block that comes at the left of expression, they should be rich. So this is, I guess, something new for you. By definition, if you don't basically put anything, here we have output rich. If you don't put anything like rich, all signals are considered as wire. But whenever you want to use some signals to assign something to them in the always block, you need to express them as rich. And that's important that you know that basically this rich does not mean that this variable is gonna synthesize to the register. So basically, whenever you define something as rich, it can be synthesized as a register or the flip-flop, or it can be synthesized latch, or can be synthesized as a wire, basically. So it depends in the end that how you model and how you assign value to that rich, that we will see later also. Okay, so in your, basically, you can also have asynchronous or synchronous reset. So I guess you know that reset signals are used to initialize the hardware to a known state. It could be 0 or it could be anything, but basically the initial state of the hardware. And it can be asynchronous reset. Basically, whenever you activate the reset, it's gonna reset your signal, reset your circuit. And it's not waiting for the basically clock. So whenever it is asynchronous, it's kind of, it's faster because you don't need to wait for the clock rise or clock fall, depending on how you define your flip-flops. But at the same time, it has some sensitivity to glitches that may have some metastability issues. We will also see later in lecture 6B about glitches. And your reset could be also synchronous. So whenever you want to reset or initialize your circuit, you have to wait for your clock. So for example, if your clock is on posage, you need to wait for the posage clock. And then if the reset is activated, you will basically reset your circuit. So it is kind of easier to implement, but the problem is that it should be, it has some latency. You need to wait whenever you want to reset. So sometimes if you want to quickly reset your signal because of some safety issues, maybe a synchronous reset is not a good option. And actually, this asynchronous versus synchronous state, it can be also broader. So here we are talking about the overall circuit you are designing sequential is synchronous, but the reset can be asynchronous or synchronous. But you can also, broader this, concept to, broader concept, which actually you can have the whole circuit that you design can be asynchronous or synchronous. So whenever the circuit is asynchronous, sequential lock, basically we saw is an asynchronous machine. State transitions occur when they occur. So whenever you want to transit to a new state, you don't wait for anything, you just transit. So you can observe, you can imagine that is quite, it can be faster. But the thing is that most modern computers are synchronous machines. And the reason is that basically it makes design much easier and more reliable. So, and you can imagine there is a trade-off. So one is easier, more reliable, the other one is faster. So, but yeah, we will assume synchronous systems in most of this course. Okay, so now let's see how we can implement asynchronous reset in a Verilog code. So basically in the always, you should put, at sign negate reset if you want to, also have an asynchronous reset. So here you will enter the always block whenever a rising edge of clock happen or a falling edge of reset happen, both of them. So when you enter the always block, you first check if the reset is 0, because activating reset in this special circuit means that the reset is 0. So you check if reset is 0, and if it is, you initialize your Q to 0. And else, it means that basically the reason that you enter this always is not because of reset. That was because of rising edge in clock. And basically you will just instantiate the D to Q. Sample D to Q. So in the always block, it's always good that you have a begin and end statement. So it's not always needed. For example, here it's not needed since we have this if else statement. So it's always, considered as a one basic block. So you don't need to basically put begin and end, but it's always good for readability and also to make sure that you don't make mistakes. And here actually we can see that basically we first check the reset, because if reset is set, Q should be set to 0. And this is an asynchronous reset because, as I said, because we don't basically wait for the clock. So how we can implement synchronous reset? That's easy. Basically, your always should always be only synthesized on postage of clock, and you will just check the reset value. When you enter the always, you first check if reset is 0 or not. But since when, the moment that you are checking that reset is 0 is when the clock, the rising edge of clock happens. So it's kind of synchronous reset. And you can also have enable for D flip-flop. Basically, whenever enable is activate, you will sample the D to Q. So usually enable also happens synchronous. So here you can see that basically in the sensitivity list of always, we have postage clock and neg-edge reset. And basically when we want to write, store the D, we check that if enable is activated. Okay, and if you want to define D latch, the difference between the D latch and D flip-flop is that basically it is enabled when by the level of the clock, not rising or falling edge of the clock. So you put always at clock and D, so all the basic inputs, and basically if clock means that. Yeah, if clock means that if clock is 1, your latch is in transparent mode, and basically you put D inside Q. So here you can actually see that. So we are saying that if clock, Q is D. And we don't say if clock is 0, what should be the Q, which means that it should store the value. So that means when I was saying that basically when you implement something, define a variable as range, basically why something it can be synthesized latch or flip-flop or wire. Here, since you are not saying what is should be stored or what should be the Q when clock is 0, basically you are saying that Q should have this possibility to memorize if clock is 0. Which means that you are having latch. So, okay. So as a summary, sequential statements are within an always block, and the sequential block is triggered when a change in the sensitivity list. Signals assigned with an always must be declared as rich, and we use non-blocking assignment and do not use assign statement within the always block. There are also some, I'm gonna quickly discuss about some basics of always block. So basically you can have as many always block as you want in your code. But the important thing is that you should make sure that you don't assign to the same, variable in different always block. It is, it's not allowed. So here also, this is exactly what I already covered. So here we are saying that when we have a postage of clock, Q is D, but we don't say what happens when the clock is not rising. The value of Q is preserved, remember. So it means that this always, the range variable that we define here should have some basically ability to memorize, which here, because we are activating that with postage of clock, it can be basically flip-flop. But an always block does not always remember. So for example, in this example, you can see that we explain all the different scenario. We are saying that so in the always sensitivity list, we are putting everything that is related at the right side of the expression, and also we consider as the input. So here we have one expression if, which is checking the inv value and also data. So these two are important as it's to put in the sensitivity list. And we are saying that if inv is 1, result is negation of data, but if inv is 0, basically result is data. So you are saying everything that can happen with result. So this is exactly is a kind of combinational circuit. So here with your always, you are not defining a sequential circuit. This is actually a combinational circuit. And this basically output range result is not going to be synthesized as latch or D flip-flop or anything. It's going to be synthesized as wire, which is going to be driven by by this combinational circuit. Is that clear? Okay. So, an always block define combinational logic if all outputs are always continuously updated. It is important. So, and also all right-hand side signals are in the sensitivity list, as I said in the previous example. In order to not make mistake, you can use always at a star. So whenever you write into your code, always at a star means that your basically the sensitivity list of that always includes everything, which is important. So that you're gonna define combinational logic, but you should always make sure that all outputs are always continuously updated. It's also important. So basically, that's the second important thing. All left-hand side signals get assigned in every possible condition of if, else, and case blocks. So it is easy to make mistakes and unintentionally describe memorizing basically elements like latches. So your synthesizing tool like Vivado is gonna make you, give you some warning. And basically it's always good to check the warning. Because the expression is that when I'm synthesizing this circuit, I need to add some latches. So basically if you know what you are doing, that's fine. But if we don't know what we are doing, we need to double check and fix our code. Okay. So let's have a very quick kind of quiz. So this code, is defining sequential or combinational logic? Any idea? Let's have a guess. You're gonna be 50-50% hopefully correct, no? So here we have always at a star, which means that the sensitivity list is correct, right? So we have every, by saying correct, I mean probably we are gonna have a combinational circuit. However, in the statement of the always, we are saying that output A is initialized to 0. If enable is activate, we're gonna make out A to data. So we make sure that out A, we know what we want to do with out A, right? However, for out B, we are saying that if enable is activate, out B is data. But we don't say if enable is not activate, what should be the out B, which means that out B should have some memorizing characteristic. So as a result, this is a sequential circuit. Out B is gonna synthesize to latch, but out A is gonna be just a wire. How about this one? This one is easier, no? Yes. Correct. Great. Yeah, that's true. Yeah, basically we don't put enable in the sensitivity list of this always, and this is also sequential. Perfect. Okay. So basically not every time makes sense to use always. Sometimes using assign a statement is easier. So here this always, for example, is implementing a multiplexer 2 to 1. But this assign a statement also is implementing also the same thing. So you can see that writing the multiplexer with assign a statement is easier. So basically, I mean, you will decide and you will see when it makes sense to use always for combinational circuit or when it doesn't make sense, basically. But as a rule of thumb, if your combinational circuit is easy to implement, usually we prefer to use assign a statement. But when it is complex, probably you're going to use always a statement. So another good way of using, I mean, one of the good possibility of always is for a case statement, which is quite handy. For example, here you can see that the way we can, I guess, implement 7 segments. And yeah, you can see that it's easy to use case statement, switch case. So basically, if else block can only be used in always block. And the always block is combinational if all range within the block are always assigned to a signal. And basically, it's important to use the default case to make sure you do not forget an unimplemented case. So, and you can actually use case X statement to be able to check for don't cares. So some of these, that can basically guide the synthesizing tool to basically consume less hardware when it wants to basically synthesize. So you can see the syntax of case X, for example, in your lab, I guess, and also in your readings. Okay, now it's the time to see what's the difference between non-blocking and blocking assignment. So non-blocking assignment, we already see, is just, I mean, this expression. So all assignments are made at the end of the block. So whenever you have non-blocking assignment in your always, when the control flow reaches to that assignment, it evaluates the variable that needs to be basically stored to the left variable, but the assignment is not going to happen on that time. It's going to wait until the control flow stops. So, and in this, for example, always, the control flow of the always is going to stop by the end of this always. So when you reaches to the end and you want to basically go back to the sensitivity list. So all the assignment happen on that position. But I mean, yeah, in different, we have blocking one, which basically block the assignment. So here, for example, I equals to 2 binary 0, 1. It should first happen. So basically, the variable age is going to be set to 0, 1, and then we are going to move to b equal to a, which that's important here. So in this non-blocking assignment, we have this a equal to, I mean, non-blocking to variable 0, 1. And then we want to assign, again, non-blocking a to b. So what would be the final value of b in either of non-blocking assignment or blocking assignment? So in the left side, because basically, as I said, the assignment of A is not going to happen when you on the moment that we evaluate the assignment in blocking in the always block. As a result, for B, when B is going to evaluate the variable A, it's going to read the previous, I mean let's say absolute or the previous value for the A. So B is going to be A, but A is not, but that B is not 0, 1 basically in the left side. But in the right side, A is going to be 0, 1, and then we move 0, 1 to B because of this blocking assignment. Is that clear? I hope so. Okay. Yeah, basically a blocking assignment is similar to sequential programs that you have in C+ programming or other languages, I guess. So non-blocking statement allow operating and old values enable easy sequential logic description. So whenever you want to basically define sequential logic, it's always a good practice to use non-blocking assignments. And as I said, blocking statements allow a sequence of operations and allow operations on immediately updated values, more like a software programming language. So that's actually a very nice point to see. If the sensitive list of the always is correct, a block with non-blocking statement will eventually evaluate to the same result as the block with the blocking statement, but with different number of iterations. Let's see an example here. So all inputs are initially 0, and all of these are blocking assignments. So after we basically, if A changes to 1, so we enter this, since there is a different, let's say, in the sensitivity list, it's gonna enter the always, and all values are updated in order. So you can see the new values. Okay, this is the blocking statement. But let's see what happened when we have non-blocking statement. So when A changes to 1, again, all assignments are gonna happen, but in a concurrent manner. So the thing is that yeah, exactly. So you can see that the S variable is dependent on P. So when we want to evaluate the amount that we need to load to S, we will read the previous amount of P, which was 0. So basically, when S is being assigned, P is still 0. So because of that, we are gonna have this variable. This is the kind non-blocking assignment. But the thing is that now after the first iteration, P is changed to 1, right? So since P is also in the right side of this assignment, again, the sensitive list is gonna be activated and you're gonna enter the always block again. And then after the second iteration, you're gonna reach to the same assignment that you had in the blocking assignment. So these are some rules. Basically, whenever you have always at OSH clock, it's better to use non-blocking assignment to model synchronous sequential logic. And it's better to use continuous assignment like assign to model simple combinational logic. And for basically, we use always at a star and blocking assignment to model more complicated combinational logic. And basically, you cannot make assignment to the same signal in more than one always block or in a continuous assignment. I mean, this one is going to be basically wrong because you're assigning to A in different always. And this is also, it's not working because you have this assign statement and always, and both are going to be set to A. Actually, this one is not possible at all because when you define A, since you're using A in the always block, you need to define it as reg. But for the assignment, A should be wire. So basically, I mean, it's not possible at all. Okay, now let's see how we can implement an FSM using always block, what we already learned. So yeah, each FSM consists of 3 separate parts. Next state logic, which is essentially a combinational logic. State register that we're gonna use for, we use D flip-flops to store the state, and also output logic that can be basically related, dependent on the current state, which is Moore, or current state and the input, which is Mealy machine that you already, I guess, learned yesterday. So eventually, when you are designing, implementing an FSM in Verilog, you have to define these sequential logic and combinational circuits. Let's see how we can do that using some examples. So this is one example that you want to basically divide the clock frequency by 3. So in order to do that, you're making an FSM with 3 states. And whenever you have a rising edge of clock, you go to the next state. And after 3 states, you're gonna basically flip a variable y that can basically, so that flipping rate happen in a basically, 1/3 frequency of the normal clock that you can. So by this logic, I mean, digital design, you can divide the clock frequency by 3, for example. Which in reality, actually, we don't do. I mean, whenever you want to divide or multiply clock frequency, we don't use digital circuits. I mean, that has some analog circuits that's doing, which is very actually sophisticated and hard to implement. But yeah, I mean, for now, we want to use this as an example. So basically, this is how you define. You have 3 states. You have to code them. So one way is in order to encode your states is since you have 3 states, you are using 2 bits. So basically, you are saying that state 0 is 2-bit 00. State S1 is 2-bit 01, and so on and so forth. And so as the input to your module, you have clock, you have reset, and output D. But internally, this circuit needs some memory. So you need to define 2 reg, state and next state. A state is essentially your flip-flops is going to be exactly synthesized as your registers. But next state basically is the combinational circuit that's going to evaluate the next state. Okay, let's see. So in your state register, it should be as easy as you can see. Basically, it's always at postage clock and here postage reset. So we are saying that this is, we are assuming asynchronous reset. And that asynchronous reset also happen in the rising edge of reset. So yeah, if reset, a state is gonna be S0. By the way, defining these parameters is not, I mean, essential. These are just for better readability. You can do that or you can just ignore. So state is gonna be S0. And if reset is not activated, state is gonna be next state. Hope that's clear. But you also need to have a logic to express next state. As I said, next state is a combinational logic. So you are gonna use always at star. And it is dependent on the state and the input. But for this example, it's not, I mean, fully, I mean, it's a very simple FSM. So it's only dependent on the state. So always at the start, you have a case on a state. If we are in S0, next state is gonna be S1. If we are in S1, the next state would be S2. If we are in S2, the next state is S0. And you need to also define a default. Why is that? Because the state is 2 bits. So basically, you should have 4 cases in your switch case. So it is actually very important here to define the default state. Otherwise, your next state is going to be defined as something like latch, which we don't want that. And as the output, basically, so that was a Moore machine. So whenever we are in state 2, the output is going to be 1. So basically, we have this assign Q equal to state, sorry, whenever we are in a state 0, a state equals to S0. So yeah, and this is how we put all of them together. So you have the definition and also the always for the state register, another always for the next state logic, and assign a statement for the output logic. This output logic also can be an always, but basically, as I said, you're allowed to define combinational circuit with assign a statement with gate level, structural level, and also with, I mean, always. That's basically what you are going to decide based on the complexity of your implementation. Any question? Okay. So let's see quickly another example. Remember that smiling snail. So, and let's try to implement the mealy one this time. So in the mealy implementation of this smiling snail that we have, I guess, yesterday, we have 4 states. And whenever you are in a state S3 and the input number is 1, the output is going to be 1. Otherwise, the output is 0. Let's see how we can implement that. So we have 4 states. Again, we can encode the states with 2 bits. By the way, there could be also other encoding. There are some, for example, you can encode your states with 1 hot coding. So you're going to use 4 bits to show your basically states. This is also something sometimes have some trade-off that you can basically see which one is better. But here, as an example, we have simple encoding that we are going to use 2 bits. And so the state register is, again, so easy. We just say that, yeah, always at rising edge of clock and rising edge of reset. I mean, it's essentially the same as the previous example. And this is the logic, always that we need for the next state logic. So it is a bit more complicated because of this FSM. So in your case, you have this case on a state, and in each state, you evaluate the number. So basically in S0, if number is 1, next state should be S1, else next state would be S0, and so on and so forth, basically. So in this switch case, you don't really need to define default, but as I said, it's always good to have that, because I mean, you don't know what's going to happen, and it's going to be, I mean, you don't going to make mistakes if you always use these default cases. Okay, and for the output logic, so basically smile, we assign it when basically it should be set to 1 whenever we are the number is 1 and the state is S3. So in this example, output depends on the state and input because that was mealy machine. And yeah, again. And this is how it's gonna be look like in your example. Okay, what did we learn? So basics of describing sequential circuits in Verilog. There's always a statement needed for describing, memorizing elements like flip-flop latches. We can also use always to define combinational circuits. We also learned what the difference between blocking and non-blocking statement. So blocking a statement assigns the value immediately, but non-blocking assigns the value at the end of the block. And also we use this always block to describe FSM in Verilog, which basically essentially we need 3 circuits. One is next state logic, which is a combinational circuit, state assignment, which is going to be a sequential circuit that you have always at rising edge of clock, and output logic, which again is a combinational circuit that is dependent on the state, only state if you are designing a Moore machine, or it can be dependent also on the input as well as the state, if you are designing a mealy machine. Okay, any question? I think now is the perfect time for a, let's say, 10-minute break. We're gonna continue with timing and verification. See which ones are worth fixing. Okay. Yeah, let's continue. Is my voice okay in Zoom, Geraldo? Can you hear me over Zoom? Okay, great. Okay, before moving to this lecture 6B, are there any questions for the previous lecture? Okay, perfect. So in this lecture, we are going to talk about timing and verification. Let's see. I'm not sure if we can reach to verification part, but yeah, we will try. So yeah, there are some readings that is good for you if you want to check. You can check the slides. And so next week, we are going to also cover von Neumann model, which is important for, how we implement processor. So these are some suggested reading that you can check for the next week lecture. And as a recall, there is extra credit assignment 1. The deadline was, I guess, is still, April 1st, if I'm not mistaken. And extra credit assignment 2, yeah. You can do it if you haven't done yet. And these are some guidelines about how to review papers critically. Okay, so what we are going to learn now is about timing in combinational circuits. So we have propagation delay and contamination delay and glitches. And basically, we have also timing in sequential circuits, which is setup time and hold time, and determining how fast a circuit can operate. And also circuit verification, which is basically when you design your circuit with HDL, you want to verify that it's working or not. And that verification can happen in different levels. So one level is when you basically design your high-level HDL program, you verify it, and hopefully you will observe that it's working perfectly. But when you synthesize your circuit, then you also need to verify it. Sometimes it's not going to work after synthesizing, and you need to roll back and fix something and then synthesize. Sometimes after synthesizing, the verification passes, but when you build your circuit, it's not going to work. Basically, this verification is one of the essential phase in circuit design, and you need to do that in different steps. Otherwise, you cannot basically realize what was the problem. Okay. So there are some trade-offs in circuit design. One is area. So circuit area is proportional to the cost of the device, speed and throughput. So we want faster, more capable circuits, and also power and energy. So for example, mobile devices need to work with a limited power supply, and high performance devices dissipate more than 100 watts per centimeter square. And design time. So basically, designers are expensive in time and money. So the computation will not wait for you. So you always need to have, reduce the time to market for when you are, designing some circuit to sell. So as a result, this design time is really also important. So you can see these are different trade-offs. And basically, what you want to design and the purpose of your circuit can essentially show that how you should approach that trade-off. So one of these, as I said, important factor is circuit timing. So until now, we investigated logical functionality. So we're just saying that, truth table and how we can implement circuits. But in reality, timing is basically how fast is a circuit and how can we make a circuit faster, and what happens if we run a circuit too fast. So sometimes increasing, speed of the circuit can make a lot of problem. So basically, a design that is logically correct can still fail because of real-world implementation issues. So in the part 1 of this lecture, we're going to see combinational circuit timing. So digital logic is a convenient abstraction. Output changes immediately with the input. This is how basically we were seeing in the past. So when we have a NOT gate and A is the input, so basically A has a perfect shape when it's falling to 0. And then immediately y is gonna move to 1. This is how we were basically designing using truth table, which is very good actually. It's convenient, but in reality, it's not the case. So we have something like that. Whenever the input is gonna be rise, I mean, it has some delay, and also the output also is not gonna. Yeah, I mean, I guess there is a problem here. The y should go to 0, but anyway, I mean, there should be also some delay for the output as well. So we have this delay, and this is basically the timing of one real inverter. And you can see that basically the input is changing. It's not completely, perfect rising or falling edge. And the output is also not perfect. So we have some delays. So delay is fundamentally caused by capacitance and resistance in the circuit. So each wire and all of these, logical gates, transistors, they have some capacitance, and also you have some resistance. So in the end, you are dealing with some RC delays. And also the speed of light, is fast, but it's finite, and not so fast actually on a nanosecond scale. So your logical design is also be nanosecond scale. So basically that you will see some delay. So anything affecting this quantity can also change delay. So rising 0 to 1 and falling 1 to 0 inputs, different inputs have different delays. And changes in your environment, like the temperature, like the voltage, supply voltage, and also the age of the circuit, all of these can basically affect the timing of your circuit. So we have a range of possible delays from input to output. For example, when you are defining a two-input AND gate, so you may see that basically we are going to define different delays from input A to output, from input B to output, when we are going to rise the input A, when we are going to fall input A. All of them have different numbers. And you can actually go deeper and define different latencies for different supply voltages, for different temperature, and basically populate your data sheet. So we have a true definition. As a kind of easy abstraction. One is contamination delay, which we call it TCD. So basically, it's a delay until the output starts changing. And propagation delay, which is TPD, that's the delay until the output finishes changing. So here's an example. You have a circuit the input are A, B, and the output is Y. So when you're changing the input A, your output is gonna change. So this cross-hatching means value is changing. That's a notation, basically. So you can see that from the point that A starts changing to the point that Y starts changing, we call it TCD, contamination delay. And from the point that A starts changing and Y finally reaches to the stable state, we call it propagation delay. Hope that's clear, I guess. Okay, so basically we need these delays to calculate the longest and shortest delay path. So see this circuit, for example, this has, 3 gates. We first, AND AB, and then we have an OR gate, and then finally we have an AND gate. By looking at this circuit, you can see that we have a longest path from AB to Y, and we have a shortest path, which is from D to output. So I think probably the longest delay of this circuit is going to be determined by the AB, and the shortest delay is going to be determined by the D. So critical path or longest path, you always define it as propagation delay, because propagation delay is essentially the longer delay, because you want to wait that output is finalized. So T propagation delay here is 2 delay for AND gate and 1 delay for the OR gate. And all of them, you are using propagation delay because you want to calculate the maximum delay. And for the shortest path, you always need to calculate the less amount of latency that you may have. So the shortest path is from D, and you're gonna basically, so for D, we have only one AND gate. And then for that AND gate, you also use contamination delay, which is the, lower latency. So that defines basically the contamination delay or shortest path delay of your circuit. Any question here? Okay. So yeah, for example, so previously A was 1, B 1, C 0, and D 1. And you're gonna change A from 1 to 0. So you can see that when we change A to 0, N1 is gonna be evaluated to 0. And since N1 is 0, N2 is also gonna change to 0 because previously it was 1. And then since N2 is also 0, Y is also going to move to basically 0. So in this curve, you can see different, the propagation delay. So when we falling A, we have some latency so that N1 also falls down, and then some latency N2 falls down, and then Y. This is how we propagate delays. And for the shortest path, for example, when we move, when we change D from 1 to 0, the output is gonna move to 0. So basically, your path is on only one gate here. Yeah, this is a data sheet, for example, table for a real NAND 2 gate. You can see that we have different numbers here for different supply voltages. And also basically depending on the different temperature. And you can see that, for example, for temperature 25, we have minimum delay, typical delay, maximum delay. For temperature 85, I don't know, for 112.5. Basically, as much as you put more effort and calculate these latencies, you can populate your data sheet more and basically gives more hint to the people that are going to use your circuit. Okay, so and also the way that you implement your circuit can actually affect significantly the latency. Assume that we want to implement 4-to-1 multiplexer, and these are the latencies that we have for let's say, different gates. So the latency for NOT is 30. For 2 input AND is 60, and so on and so forth. So this is one implementation that, so basically you need to, for multiplexer 4-to-1, you have 2-bit selector. So you first need to have this selector and negation of them. And for each output, you have this 3 input AND gate. And then you need to OR them, right? This is one way of implementing multiplexer 4-to-1. So probably you cannot see, I don't know, easily, but the thing is that, so the propagation delay here is, so the delay of the inverter and the delay for the AND tree, the propagation delay from S, from the selector to the output, TPD to SY. So basically, you have the delay for the inverter, you have the delay for the AND tree input, and also the delay for the OR gate. And the propagation delay from the input D to the output, you will have only the basically AND tree and also OR delay. So it's important that you, based on each input, you know what are the gates that are gonna contribute, and just basically add those latencies. So this is another way to implement using a 3-state buffer. So you need to have these, NOT gates. But the good thing is that you're going to have basically your AND gate is going to be 2 input. And essentially, each of these AND gate is going to define the selector of that 3-state buffer. So here, when you want to calculate propagation delay from S to Y, you have the delay of the inverter, the AND2, and also the tri-state buffer. And also the propagation delay from the input to the output, from D to the Y, is only the latency for the tri-state buffer. which is less. So you can see that the way that we implement using reset buffer, we can heavily reduce the latency in both cases. Another way to implement the multiplexer 4-to-1 is using a 3-2-to-1 multiplexer. And you can check latencies later, but you can see that, for example, by this definition, we can reduce the propagation delay from selector to Y to the output, but essentially it increases the propagation delay from D to the output. So basically, that's also a trade-off, the way that you are implementing. Any question? Okay, so it's important to know that it's not always easy. It's not always this easy to determine the long and short paths. So not all input transitions affect the output. Some of these input are not, not all combinational circuits have just, a few inputs that you can easily figure out. And also you can have multiple different paths from an input to output, which is essentially hard. And actually, synthesizing tool is evaluating them. When mostly, each synthesizing tool, when synthesize your circuit, they also calculate the latency of your circuit, the critical path. So for that, they are actually calculating. But it's easy for the computer program, probably, but it's not that easy for us because we need to evaluate many different, let's say, branches. And in reality, circuits are not all built equally. So different instances of the same gate can have different delays. So in the previous example, we considered that all nodes are the same, but that's not can be not the case. And wires have non-zero delay. So we don't consider any delay for wires, but wires also, they have some delays. And with different temperature and voltage, basically that can affect circuit speeds. And the effect of different voltage and temperature can be actually affected, can affect different circuits differently. So in the end, actually can even change the critical path latency. So for example, you assume, you calculate that, for example, for temperature 25, branches, A to Y is the longest path. But when you change the temperature, that could, be different. So you can see it's not easily. And basically, designers assume worst case conditions, and they run many statistical simulations to balance yield and performance. So circuit output change sometime after the input change, as a summary. And the reason was finite speed of the light and also delay dependent on inputs, environment, and the capacitor resistors that we have. And the range of possible delays, we have contamination delay, which is the minimum possible delay, and the propagation delay, which is the maximum possible delay. And delays change with circuit design, topology, materials, and operating conditions like temperature and supply voltage. So any question about the part one? Okay. Now let's quickly see output glitches, which is, pretty cool in my opinion. So what is glitch? So glitch is when one input transition causes multiple output transitions. So in a steady state, when you change one input, the output is going to be changed to something. It's going to change or not change. But in the end, what you are assuming is that it's going to change to 0, 0, 1, or just remain constant. But in reality, many circuits, they have glitch. So when you change the input, the output is going to change multiple times. Let's see with some example. So here in a circuit in the initial state, so we have two inputs 0, 0, and another input here is 1. So yeah, the output is going to evaluate to 1, right? But assume that basically the previous version was 0, 1, 1, and now we want to change the 1 to 0. So basically we have two passes, right? From the input, let's say, name it as B. From the input B to the output, we have two passes. One of them is the slow pass, which essentially has 3 gates, and the other one is this faster pass, which we have only 2 gates. So the thing is that this is going to happen. Why is that? So when you basically move one, when you want to transiate 1 to 0, this fast pass is going to change the output to 0. But after some time, because you are also waiting for the output of that slow pass in the red line, that is going to evaluate to 1, and then the output is going to again transiate to 1. So you will see something like that in the output. So this output was 1. You will see a small glitch. Usually it's just small. It can be, it's not going to be actually completely go to 0 also. It's just reduction in some voltage and then increasing. But there is some glitch in any way. And yeah, this is glitch. Question?
Like when we want to evaluate the end of the output, now we can actually take this value because it's not glitch.
That's exactly why we, as I said, for asynchronous in the previous lecture, we're saying that about synchronous circuit and asynchronous circuits, right? So when you have synchronous circuit, and so you define your clock period enough time, long enough, so that you don't have glitch problem. So when you're sampling your input, everything is correct. And that's why we're saying that when we have asynchronous circuit, glitches can be difficult to handle. Thank you for the question. Any other questions? That was actually very good one. Okay. So, there are a few slides here, which is optional. I'm gonna move them, go over them quickly, but I'm gonna basically talk about them because it's pretty cool, in my opinion. So how we can, avoiding glitches using Karnaugh map. So you don't, I guess, yeah, Professor Mutu, I guess he didn't cover Karnaugh map. But yeah, for this 3 input circuit, Karnaugh map is going to be similar, something like that. So basically you have different, A, B, and C. These are the input. And for A, B, you have different, combinations, 0, 0, 0, 1, 1, 1, and 1, 0. And you should make sure that these are in a gray code. And basically between 2 neighboring variable, there is only 1 transition. And for C, we have 0 and 1. And in the end, in this Karnaugh map, you are gonna put those min terms as 1, basically. So in this circuit, we know that when the input are 0, 0, 0, the output is 1. That's the min term. So we put 1. And also when the input is 0, 0, 1, we have also another min term, which is again, we have 1. So yeah, that's quick explanation of the Karnaugh map. And whenever you're having a Karnaugh map, the way you want to simplify your circuit, you're gonna have some, let's say, cube that's basically, yeah, circle those cube of 1 that have 2 to the power n 1. So here, for example, this we have 2. Okay. You can see that we have 1 and 1. This is a cube of 2 minterms. And here we have 1 and 1, again, cube of 2 minterms. That it should be actually neighboring. So, and then you will also, yeah, in the end, you can simplify your circuit using Karnaugh map. The thing is that whenever you have something like this in your Karnaugh map, we call them prime. So this cube is a prime implicant, and this cube is also prime implicant. So whenever you have a transition between 2 prime implicant, you are going to have glitch. That's the way that you will understand that your circuit has a glitch. So you can see that since we have a movement here, we have glitch. So how we can fix that? Basically, you should make sure that you don't have that basically transition. So the way you add another cube, you don't really, so in order to reach to the simplified circuit, you are just need this cube of 1, 1 and this cube of 1, 1, these 2. But you are also going to consider this cube of 1, 1 to make sure that there is no, all of these prime implicant, they have overlap and there is no transition. And in the end, you're not going to have glitch. So basically, you're adding a new gate, which makes your circuit complicated and more costly. But in the end, you are fixing the glitch problem for this special circuit. I mean, that's, as I said, it's optional. You can also go over it later if you want. But yeah. So avoiding glitch. Do we always care about glitches? What do you think? That's true, but so when you don't have glitches in a in a synchronous circuit, essentially you are also you would be able to reduce the clock period. Basically, you can work faster. So in the end, also you may care about glitches. And another thing about glitches is that, sorry, glitches are very bad in terms of power consumption. Actually, one way to reduce the power consumption is to make sure that your circuit do not have too many glitches. So if you check some, let's say, optimization paths in order to reduce the power consumption, one actually path is to make sure that we don't have too many glitches. But in the end, it depends. So you may know, basically you don't care. If we only care about the long-term steady state output, we can safely ignore glitches. And that's actually up to the designer to decide if glitches matter or not in the end. Okay, are we good? So let's move to part 2, sequential circuit timing. So that's the definition of the flip-flop that we already covered. So in a D flip-flop, we have 2 definitions: setup time, hold time, and actually 3 definitions: aperture time. So setup time is the latency that the time before the clock age. So setup time always consider before age of clock. So time before the clock age that the data, I mean input data, must be stable. So here in this example, we have, D is the input. And basically this is the setup time. We should make sure that we don't care how much glitches or anything happen, or I don't know, something happened to D. But by definition, before this setup time, D should be stable. Otherwise, we are not going to be in a stable situation. And hold time for T flip-flop is the time after the clock age that data must be stable. So basically, we are not allowed to change the D after rising edge of clock until T hold. And basically addition of setup time and hold time, we call it aperture time, which is the time around clock age that data must be stable. Is the definition clear? Cool. So basically, if D is changing when sampled, that, as I said, metastability can occur. So this is one example in a real study that, when we have a falling edge of clock, the clock was, it was in the falling edge. And so basically the input was changing after the setup time, and you can see that the output is non-deterministic. And so you should make sure that these things does not happen. It can be also because of the hold time. So it's not clear what was the main reason for that, but anyway, any of these, violation can make your design doesn't work correctly. Okay, so here also we can define contamination delay, which is the contamination delay clock to Q. So whenever you are having assume that here we are working on rising edge of clock. So the earliest time after the clock edge that Q starts to change, we call it contamination delay clock to Q, or TCCQ. So basically the output is not is unstable. And we have propagation delay from clock to Q, TPCQ, which is the latest time after the clock edge that Q stops changing. So basically Q is going to be stable. Yeah, similar kind of definition to combinational circuit. So as I recall, sequential system design, there should be some D flip-flops or register and some combinational logic, right? So you have to make sure that you're basically satisfying all of these time definitions. So multiple flip-flops are connected with combinational logic, and clock runs with period TC, which is cycle time. And basically, we have to meet timing requirements for both register 1 and register 2. Otherwise, your circuit is not going to work correctly. So let's ensuring, as an example for R2. So basically, we have two timing constraints, right? Setup time and hold time. So we should make sure that whatever is going to happen for Q1 and also this combination logic to define this D2, because D2 is the input for this flip-flop, right? So what's going to change D2? This Q1 and this combination circuit, right? So whatever is going to happen, basically we don't care. But before setup time of the next rising edge of clock, D2 should be finalized and should be stable. And after the clock cycle, again, we're going to having changed in Q1 and combinational circuit, they may change D2. So we should make sure that D2 is going to be stable after T hold time also. Is that clear? Okay. So basically, it means that there is both minimum and maximum delay between two flip-flops. So let's quickly, go back here. Basically, what is important for setup time is actually the longest delay. So the delay you have here for Q1 and also this combinational circuit, it's important that you consider the maximum delay of them to make sure your setup time is going to hold. And for T hold, because it's going to happen after the rising edge. So we may, after the rising edge of clock, we're going to have a quick change in Q1 and also quick change in, combinational circuit. So D2 is going to change because of the shortest path latency in this part. So we should make sure that the minimum latency of this circuit is also, longer at a certain amount. Which is actually very interesting. So you don't only care about the longest latency, but you also care about the minimum latency of your circuit. Okay, so yeah, basically, if the combinational circuit is working too fast, then the basically T hold is going to violate. And for setup time, we should make sure that our circuit is not too slow. Okay, now let's make some calculation for setup time. So the safe timing depends on the maximum delay from R1 to R2. So this is the figure that I was going to use here. So whenever you want to define the clock cycle, right? So you have basically your clock cycle period should be longer as TPCQ, which is the propagation delay from clock to Q. As I said, whenever you want to calculate the setup time, you always need to work with the longest delay, right? So for the flip-flop, you're also going to use the PCQ, which is the propagation delay. You're not going to use contamination delay. So TPCQ and also the propagation delay of that combinational logic and the T setup. So basically, your clock cycle should be longer than this. True? And in the end, basically, this propagation delay of the for the flip-flop and the setup time is the wasted work, because that combinational logic is doing something useful for you, but those just something that we need to add to make sure that our circuit is working correctly. So we call them sequencing overhead, amount of time wasted each cycle due to sequencing element timing requirements. So as an example for this circuit, basically the setup time, when you want to calculate, you need to use the critical path latency, as I said. So the propagation delay of the combinational circuit is the delay for the critical path. So that's important to use the longest path. So if the critical path is too long, then the design will run slowly. So when sometimes you are designing a sequential circuit and in the middle you have some combinational circuit, and that combinational circuit is doing a lot of work. So that can make your frequency slow. At the same time, sometimes your combinational circuit is so simple and you're not doing something useful. So basically that can you can work on a high frequency, but the amount of work that you are doing by each clock cycle is a little. So again, that's also a trade-off, how you design and essentially how you pipeline your circuit, which is something that you will learn later in this course about, how we pipeline processors, which is essentially related to this topic also. Okay, now let's see about hold time constraint. So safe timing depends on the minimum delay also from R1 to R2. So here, since we are gonna consider the minimum delay, we need to basically consider all the, contamination delays, the fastest pass. So basically D2 must not change until T hold after the clock. So in order to calculate that, we are saying that TCCQ, which is contamination delay from clock to Q, plus contamination delay of the combinational circuit, it should be greater than T hold. Okay? So essentially, the delay for contamination, contamination delay of your combinational circuit should be longer than T hold minus TCCQ. You're just, moving this expression around. So, which is, as I said, it's interesting. So we need to have a minimum combinational delay. Otherwise, our circuit is not going to work correctly. And you can see that basically T hold does not depend on TC. So whenever you are saying that setup time is not hold, basically what you can do is decreasing clock frequency. You can basically make your clock period longer so that you make sure that setup time is you meet that constraint. But for the hold time, the thing is that the definition does not relate to clock. So, and actually it only depends on the, let's say, the contamination delay of your combinational circuit and contamination delay of your flip-flop. So if you have problem with hold time, what should we do? What do you think? So if you observe that basically you cannot meet your hold time, what you're gonna do? Again, as I said, for setup time, we are gonna make our clock slower, but what we can do for the hold time, please? Make it 0. Which make it 0 to for what? For the hold. Yes. True. Yes. You should redesign your combinational circuit, and essentially you may need to add logic to your combinational circuit to make it longer so that your design can work, which we will see in an example also. So that's a summary. So for sequential timings we have T contamination delay, CQ, and propagation. These are for flip-flop from clock to Q. And also we have combinational logic delay, which can be contamination delay, which is the shortest delay. And also the propagation delay, which is the longest, or the critical path latency. And we have T setup and T hold, which are essentially important for flip-flops. And we have TC, which is the clock period. So these are, important parameters for a sequential circuit. So let's analyze the timing here. So here, as an example, you have 4 flip-flops, A, B, C, D, and also 2 flip-flops in the right side of your circuit. And you have 3 gates, right? And these are the latency. So for simplicity, we consider that all gates have basically per gate, they have this propagation delay of 35 picosecond and contamination delay of 25. So let's make some calculation. Anyone wants to calculate the propagation delay for the combinational circuit? So for the combinational circuit, basically the longest path is from A to Y prime, right? So you're gonna add, let's say, 3 propagation delay. So we have, any of them is 35. So 3 times 35 is 105 picosecond is the propagation delay of your combinational circuit. So what is the contamination delay of your circuit? So there are 2 passes that they are fast. One is basically C to X prime, and the other one is D to Y prime. So essentially, both of them, they have only 1 gate. And you are going to use the contamination delay of that gate, which is 25. So basically, TCD is also 25. So now we have these things, we can check the setup time constraint. So clock time, your clock period should be longer than TPCQ. So TPCQ is 50 picosecond. And the propagation delay, which is 105, and also the setup time, which is, in our example, is 60. So overall is 215 picosecond. So your maximum clock's frequency can be 4.65 gigahertz. Now let's check if we can meet the hold time. So for the hold time, TCCQ, which is contamination for clock to Q, plus T contamination delay for the combinational circuit should be longer than T hold. So you'll see that 30 plus 25 is 55, which is not greater than 70. So basically, our hold time analysis failed. So what we can do, we basically, one simple way is to add gates. So we add 2 buffer gates there just to manually increase the latency for the shortest path. So if you repeat the experiment, basically you will see that propagation delay is not going to change, but the contamination delay is going to change to 50 because you have 2 gates now. And so since propagation delay is not changed, your frequency is not changing, but for the whole time now, because the basically contamination delay of your circuit is increasing to 50, now that equals to 30 plus 50 to 80, which is greater than 70. So we pass the whole time constraint. Was that cool? Okay. To make matters worse, clocks have also delay too. So basically, the clock does not reach all parts of the chip at the same time, which we call it clock skew. There is a time difference between 2 clock edges. So here is an example. This is the clock source in the top. And you can see that basically in point A, we have the same, exactly the same clock as the clock source. But in point B, we have some skew in our clock. So they are not completely aligned. And this is an example, the study of the alpha microprocessor that is essentially showing the clock skew spatial distribution. So in different parts of the chip, we have different, we have different skews in clock. So let's revisit setup time and hold time constraint. Now we have clock skew. So what is important here is that for setup time, you need to add that basically clock skew. Since your clock cycle should be longer than propagation delay of your propagation of your clock to the Q, and also propagation delay for your combinational circuit and T setup plus T skew, because your clock may transient later. Let me show here. So for the setup time, it's important how long does it take, right? So if this clock 1 happens later, a bit, we have some skew delay in clock 1. We have some delay in TPCQ, some delay in PD, and also some delay. So in the end, we are going to add T skew for the setup time. So we call it T setup effective, basically, when you add T setup with T skew. And the same thing for the whole time, because the skew can also happen, earlier, right? Which makes everything worse. So we were saying that for the whole time, when basically this Q1, so when the clock is happening, Q1 is going to change, and this combinational circuit is going to evaluate new value, and this D2 may you may have some problem in the whole time. So D2 is going to change. So since we can have a skew, actually this clock can happen earlier than this one. So essentially, it can reduce your hold time. So in the end, your need to TCD plus TCQ should be greater than T hold plus T skew, which means that we always need to add this T skew to the hold time and setup time. Okay, yeah, so skew effectively increases both T setup and T hold, and designer must keep skew to a minimum. Requires actually intelligent clock network across a chip. Actually, one of the important part of design, digital design circuits is how we network the clock. And there are many different ways and study and how we can effectively network the clock. One important, well-known way is to using H3. That basically you always make H to continue your, basically to interconnect your clock. But that's actually one of the also research study still that how we can network clock in an efficient way so that we can minimize the clock skews. Okay. Any question? I guess I'm not going to start circuit verification because we don't have enough time. So we still have, I guess, 3 minutes, 4 minutes. So if you have some question, maybe I can take. Just a last call. Are there any questions? Okay, so if there is no more question, I wish you all the best for the weekend and see you all next week.